last laboratory exercises, we are covering the first two implementations, and on the second one, the other two implementations. And at the end, you will submit this report, so you don't have to write the report on the actual course, but later on you have time to prepare the final report. Okay. We will continue from the last lecture. So on the last lecture, we have introduced the concept of these digital signal processors and their basic idea about their architecture. And now we will continue with more details. The architecture that will be described and introduced on the lectures is like a predecessor of this actual DSP that you are using on the exercises. It is called, the name of this DSP is Analog Devices DSP 21XX, so 21 something, and the original architecture was from something like 90s, 90 something. But the basic concepts are the same, and they are inherited in all of the all of the contemporary DSPs. We have shown a little bit already about this internal architecture. This is the block scheme of this DSP. It has several executional units, 3 in particular: arithmetic logic unit, multiply and accumulator, or multiply accumulate unit, and a shifter unit. These 3 units, each of those is dedicated to a particular set of assembler instructions. We will show later on the examples of assembly instruction executed in this execution unit, in this one, or in that one. The arguments of these execution units are located in dedicated input registers. So this ALO, it has X and Y registers, so for the X and Y branch. At the entrance of this unit, we have these dedicated ALO registers. The same is for make unit, the same is for the shifter register, for the shifter unit. Data finally is fetched or stored from RAM, from data space. This data space, data RAM, is 16-bit wide, so it is organized on word level, not on byte level. And each time I access one location from the memory, I fetch 16 bits of data. And another static RAM is used for program storage, and it has 24 bits word. Why? Because the instruction word is 24 bits wide for this DSP. The actual DSP that is used on laboratory exercises in your simulation has instruction word that is either 32 bits wide or 16 bits wide. So 32 and 16. But these instructions are packed in a packet that can be executed in parallel. So for example, you might have a 32-bit ALO instruction combined with 2 load or store instructions, and these load or store instructions are 16-bit encoded. So altogether you have 64 bits of instruction that is fetched simultaneously from the program cache memory. And since these instructions are independent, they don't have any hardware collision in the sense of resources, they can be executed in parallel. So this MAC instruction, multiply accumulate, that is encoded with this first part of 32 bits, and this load or store instructions can be executed in parallel. And the idea is that this load or store, what it does, it either fetches data from data memory and places this data into these input registers of executional units. Simultaneously, executional units use the already fetched data in these registers, perform the ALU operation or MAC operation, find the result, and the result is then stored in this dedicated result register. So each of these units has its own dedicated result register. And finally, if I want to store the data to the memory back again, I have to use this fetch and store unit to transfer data from this register over data bus back to the data memory. And typically in applications where DSPs are used, you need 2 arguments for each of the instructions. Not a single argument, but 2 arguments. And for that reason, ideally, you would like to fetch 2 data values in a same cycle. And the example why I need this kind of double data fetching is shown here. So if I want to implement finite impulse response filter, I need to fetch filter state, which is actually delayed input sample value, delayed by 0, by 1 sample, by 2 samples, and so on. So these are the states of the FIR filter, and I want to fetch the coefficient of this filter. And once I have these 2 values, I multiply and accumulate this set of products. And to achieve this kind of parallel data fetch from for 2 arguments, I need 2 data spaces actually. And that was shown here. So I have this data storage. I can fetch 1 argument from this data storage, from data memory. But at the same time, I can use this program memory to fetch another data value. In particular, I can fetch, for example, filter coefficient from this program memory. And since these buses are independent, I have independent address and data bus for data memory, independent address and data bus for the program memory. I can do this simultaneously. And of course, since I have a shared, let's say, data or program memory here, the question is, how can I fetch simultaneously the instruction from program memory as well as data from the same memory over the same bus? And it is done in a way that the actual architecture of this program memory enables 2 fetches in 1 cycle. So in the same cycle, it can fetch the instruction code from program memory, but in another half of this cycle, it can fetch data value from the same memory over the same data bus. So for the programmer, it looks like the instruction fetch and data fetch are done simultaneously, are performed simultaneously. And these buses are shown in detail here for this very simple DSP processor. So you have 2 data buses, these 2. So program memory data bus, data memory data bus. So these are 2 data buses, and these 2 are 2 address buses. Program memory address bus, data memory address bus. Of course, this program memory address bus is connected to the program memory, static memory. Data memory address bus is connected to data memory. Okay? And the output value that is addressed by one or the other of these 2 addresses is then forwarded to corresponding data bus, from program memory to the data bus of the program memory, and from the data memory to the data bus of the data memory. This one is 16 bits wide because the native argument width is 16 bit. So the data path is 16-bit wide for ALU, for Mac, for shifter. So for that reason, the data memory data bus is as well 16 bits wide. So to be able to fetch the whole short value from the memory. At the same time, program memory data bus must be 24 bits wide because the instruction is 24 bits. But if you use this program memory for data fetch, for example, for fetching the coefficient of the filter, in this case, I use only 16 bits of this 24 bits value. So 8 bits are discarded or not used for data transfer. But if the instruction is transferred over this program memory data bus, then all 24 bits are used. So how to address these memories? In order to be able to perform efficient addressing of these two memories, of these two spaces, program memory space, data memory space, I have two address generators. And these two address generators are capable of generating two independent addresses. One is addressing, for example, this one, data address generator 1. It can generate the address for data memory, this data memory address bus. In this particular case, the data space is only 14 bits wide. So 16,000 location, it was sufficient for this DSP. Because the actual memory was only 1 kilobyte, let's say. For the simplest, for the first version of this DSP, they had only 1 kilobyte of memory for data space. Later on, it was extended for the more modern versions of the same architecture, and this data was then maybe 4 kilobytes or 8 kilobytes, something like that. And the program memory for the first version was only 2 kilo instructions. So 2 kilo times 24 bits. But nevertheless, the address bus was 14 bits. So hypothetically, it could address 16,000 locations in the program memory as well as in data memory. And the other address generator, number 2, it can be used to either address data memory or to address program memory when I need to fetch data from program memory. Because when I need to fetch the instruction from program memory, then the address comes from program sequencer. So program sequencer generates the effective address for instruction fetch, and this comes either from program counter or from interrupt controller or whatever. We will show this program sequencer later on in more detail. So the idea is, if I'm in this phase when I'm addressing the instruction from program memory, this address comes from here, 14-bit address. And if I'm in the second phase when I'm addressing the data from program memory, the address comes from this data address generator number 2. Okay, and just in order to be able to perform parallel operations, fetch and execution in one of those units, these two units operate completely independent of the ALU, make, or shifter, because they have a simple ALU inside of this data address generator 1 and 2, and this simple ALU is sufficient to update the address. So if we want to increment the address by 1, the pointer to the memory, to increment by 1 or to decrement by 1 or whatever, by 2 or 5 or whatever, you simply perform this modification within this data address generator, as it will be shown later in detail. And for that reason, I can perform modification of the pointer, of the address, simultaneously as I am doing some kind of useful mathematical operation in one of the 3 executional units. Hypothetically, all of these 3 units could function in parallel as well, because they have input registers, they have dedicated output registers. So theoretically, I can have a parallel instruction that would utilize some ALU operation here, some make operation here, and some shifter operation here. But it cannot be done because this 24 bits of instruction is not sufficient to encode all of these operations that you would need to employ all of the 3 units simultaneously. So 24 bits is sufficient for only one of those 3. So actually, I execute either AL operation, or make operation, or shifter operation, not some kind of combination of those. So one of the 3 is executed, but it can be executed in parallel to address modification. So data fetch or storage, data store, as well as address modification can be done in parallel with one of these 3 instructions. Okay. Just as a remark, there are alternative architectures of DSP processors which are trying to actually employ all of executional unit at once. So in this case, they have really very wide instruction word. So the abbreviation very long instruction word is used to describe this architecture. VLIW. So this is very long instruction word DSPs. They have instruction words which are 128 bits wide or even 256 bits wide, because they want to really employ all of the executional units at once. But nevertheless, you still have a bottleneck in this case, and the bottleneck is the data throughput. Because if you want to supply input arguments for all 3 units, you cannot do this, because you have only 2 buses, 2 data spaces. You can only fetch 2 arguments, or maybe fetch one and store the other. But if you want to have a 3 parallel operation, how can you do this? Because then you have 6 arguments that are needed for these operations. And this would require even more parallel data spaces to be able to fetch all of this data simultaneously. So the idea is this kind of very long instruction word architecture, it makes sense only if these executional units have additional data registers that can be used as arguments at the input, and which can be used also to directly store the result of the operation to one of these data registers. So this architecture is usually based on some kind of data register file. So you have like a universal set of registers, 8 or 16, which can be used as an input argument or as a result for all of these parallel executional units. And in this case, you can maybe efficiently encode some application, some algorithm, which is rather local, which uses the result of previous instruction as an argument of the next instruction. So if you don't have really some kind of a large data array that must be processed in parallel independently for each of the units, then you have the bottleneck, because you cannot get all of this data simultaneously. But if the data is locally stored in the registers, and if these 16 registers are sufficient to enable implementation of this algorithm, then it's okay. Then all of these units can work in parallel. Okay. So going in detail, so this second block scheme shows only these most interesting parts of the architecture: data address generators, ALU, make, and shifter, as well as program sequencer that generates the instruction address. Okay, now we'll go in detail to each of these 3 units: ALU, make, and shifter, as well as data address generators. At the end, we will also say a few words about program control. So ALU is the, I would say, maybe the most simple one. As I said, it has dedicated input registers for the X branch and for the Y branch. Actually, I have here 2 registers, AX0 and AX1, 16 bits wide. and I have again two registers on the Y branch, AY0, AY1. I can use any kind of combination of these four registers. For example, AX0, I want to add it to AY1 or whatever. And as an alternative to this left branch, I can also use the argument coming from the result bus. Result bus is connected internally to all of the three executional units. So output registers of ALU, output register of MEC, and output registers of shifter are all connected to this result bus. And then I can use as a left argument any of those output registers on the left branch of ALU. On the left branch of ALU, I can maybe invoke MEC register 1 or 0 or 2. It has three output registers. Or shift register output register is SR0, SR1. I invoke one of those as an argument for the left branch of our unit. Okay, so this is this version of instruction where this MUX is in the left position. I take this result register as the left argument. For the right argument, instead of using A1, AY0, AY1, I can use feedback register, AF. And this feedback register is the same as result register of ALU, but exactly if I want to combine several assembly instructions where the previous instruction computes the argument for the next one, then instead of using this register, I can store the intermediate result here in feedback register and use this intermediate result as a right side argument of our instruction instead of AY0, AY1. So these two 16 bits arguments are fed into the actual ALU unit, which performs any of the ALU instructions. And it also has one input flag, carry input, and 6 output flags. 0, negative carry, overflow, sign, and Q. The last two are used to implement division. To implement division on the ALU unit, I need these two last flags, AS, AQ. Okay, and then examples of instructions. Do I have examples here? Okay, examples. The idea is that the assembly is written in algebraic form. So it is not typical as for other processors where you have this mnemonic, for example, add whatever, AX0, comma, AY1. So instead of this mnemonic-based syntax, which is commonly used for most of the processors, the company Analog Devices decided to use this algebraic form of assembly instructions. Why? Because the users of these DSPs are some kind of scientists, and they know mathematics, and this kind of mathematical expression is much more meaningful to them than this kind of mnemonic-based assembly instruction. So the actual assembly code would be AR is equal to AX0 plus AY0. The second example shows the activation of this result for the left branch, result register. This MR1 is the result register, the middle register of MEC unit. We'll show how this MEC unit looks like later on. So this is 16-bit wide middle register of MEC unit. And for example, I compute exclusive OR, XOR, to the AY1 value. And I store the result not in AR, but in AF register. Then another example would be AR equal to AX0 plus feedback register. So I activate this alternative right side branch, right side argument with this feedback register, computed maybe from the previous assembly instruction. And final example is conditional execution of assembly instruction. It is very nice feature because on a conventional architecture of some microcontroller or CPU, so the condition is you only use for branching. So you say if condition is satisfied, then jump or jumps out in something. In this case, you can add this condition in front of assembly instruction. And this means that if condition is satisfied, the instruction is executed. If not, it simply is no operation is executed. So nothing is executed. Only one wait state, I would say. And do you know why would this kind of approach be much better than really branching? What is the advantage of using this kind of assembly level conditional execution? The main problem with branching, especially with all modern architecture, is with pipeline. Because all of these modern CPUs, they use this pipeline, and this pipeline means that the execution of the instruction is separated into phases. In this particular CPU, on this DSP, there are only 4 phases of execution. 4 microcycles, let's say, which the first one is instruction fetch, then I guess decode, and then they have the fetching of the arguments, and actually, finally, execution of the instruction. But once you have conditional execution, then you have the problem. I have to calibrate this smart board just a second to be able to write. For simplicity, we'll only show with 3 phases. So fetch, decode, execute. And these 3 phases are executed in a sequence. Fetch, decode, and execute. So for instruction, let's say instruction 0. Then the idea is, if I want to perform the same for the next instruction, I would do the fetching immediately after the instruction 0 was fetched. Because the fetching unit is completely independent of the execution unit of the decoding unit. So there's no reason why I should not try to fetch. So this is fetch 0, this will be fetch 1. Fetch 1, decode 1, and then execute 1. 0, 0. So there is no interdependence between these 2 instructions. So idea is I would immediately start fetching from the program memory another instruction, next instruction, as soon as the instruction 0 is fetched. Because the instruction is placed into the instruction register and is being decoded by the decoder unit of the CPU architecture. Then the same is with instruction 2. Instruction 2. So I have fetch here, fetch 2, decode 2, yes, and finally execute 2. And for the programmer, it looks like the CPU is executing instruction in one cycle. Because immediately after executing instruction 0, I have execution of instruction 1. Then I have execution of instruction 2. So for the programmer, it looks like the CPU performs each of the instructions in a single cycle. But actually what it does, it performs 3 operations, fetch, decode, and execute in a sequence. And it works very nice, fine, as long as you don't have any kind of dependencies. For example, if this E2 instruction depends on the result of E1 or E0, then I cannot do the fetching. And exactly the problem is with jumping, conditional jumping. Why? Because, for example, some other instruction sets the condition. Just for simplicity, let's say it sets 0 flag. So the result of our instruction is 0. The output value in AR register is 0, but the flag 0 is set. This flag 0 is the first one, AZ is set. And then you have here, for example, conditional jump. Jump if 0. Jump if 0. But how can he fetch the instruction here since he doesn't have the condition? Condition is set only here. So at this time instance, I would have valid condition in the 0 bit. And for that reason, I cannot do the fetching, decoding of the next instruction because I don't know what is the next address. If it is a normal program counter +1 or if it's some kind of branching address. And for that reason, if this instruction is really conditional jump, then I have to do two NOPs, two no operations. I have a stall in the pipeline. I have to wait until the condition is finally set, and only then I can fetch the next instruction from the proper address, from the next address or from the branching address. And to avoid this, you don't do the branching. So instead of using branching, you simply, based on this bit, execute instruction 1 or not. So you always fetch another instruction, first up the I0. So this I1 is conditional instruction based on the condition set in the previous instruction. This condition is set here, but what I do, I simply do the execution of instruction 1 or not. That's the idea. So it is not a branching, but simply final phase of A1 is either executed or not. That's the only effect of this conditional execution. Of course, it only makes sense if the condition is really determines only one single assembly instruction, whether it is executed or not. If I really have to jump because the whole subroutine must be executed or not, then I have to jump. So this it makes sense only if this condition really determines one instruction whether it's executed or not. Okay, so this is this conditional execution. Conditional execution. Altogether, we will see later on there are 15 different combinations of this condition. So less or equal, greater or equal, 0, carry, not carry, blah, blah, blah. So altogether there are 15 different combinations of conditions. And the idea is, if I have 15 combinations, the last combination will be unconditionally. So I have 16 combinations. So I use only 4 bits in the instruction code to define whether or not this instruction would be executed. So if this unconditional set combination is chosen, so it is always executed. But if one of those conditional execution is selected, then only if this condition is satisfied, the instruction will be executed in the final phase, in the execute phase. Okay? So this kind of conditional execution at assembly level is very important for pipelined CPUs. And to be more illustrative, modern CPU cores have the pipeline depth of 14 levels, 20 levels, not 3. So they would separate each of the instruction into 20 phases. And each of these 20 phases somehow depends on previous instructions. And in this case, the CPU core would automatically insert wait states into the pipeline as soon as it resolves these dependencies. So it knows that maybe the next instruction depends on the final phase of the previous instruction. In this case, it has to wait. So it inserts wait state into pipeline until all of these conditions are met, and only then it can execute the next instruction in sequence. Sometimes this is done in hardware. So this pipeline controller, as a part of architecture, does all of this checking of interdependencies between one instruction and the other instruction. But of course, since you have enormous number of combination of instruction, this hardware is very complex. It must identify all the possible combination where this pipeline not collision, but stall can occur. And for that reason, it complicates the hardware implementation. So this pipeline controller requires enormous number of transistors to implement, and of course it works slowly. It limits the maximum frequency that CPU operates. And then the hardware engineers found the solution. So why bother with this in real time, at the executional level? Why don't you prepare the input code in such a way that never something like that would occur? So the idea is to have a assembly level preprocessor that takes care of all of these potential stalls. So it will automatically insert no operation where it's needed. So when he knows exactly that this argument is needed in the next instruction and it is not available because the depth of the pipeline is not the same for all of the instruction, then it must synchronize by adding NOP operation in between. And this kind of architecture is called visible pipeline. So they call it, the pipeline is exposed pipeline. And, for this case, when you have the hardware that takes care of the pipeline, it is invisible pipeline. Because for the programmer, it doesn't matter how he combines instruction. The hardware will take care that the next instruction takes the proper argument of the previous instruction. But with this exposed pipeline, they say it's not something that we can implement in hardware. It's too complicated. Let's put it to the preprocessor phase. So pre-execution time, you must ensure that everything is synchronized in time exactly as you want. So in this case, you don't need to implement this hardware at all. The codes at the input are already prepared and the execution is performed as desired. Okay. Then just few additional features of this ALU. First of all, it has so-called saturation mode. So this ALU, you can activate this saturation mode in one of the control registers of the CPU. And the idea is, for example, it is illustrated here on a 4-bit value. Let's say that you have 2's complement 4-bit value, and you add two values, 4 and 5. Of course, the result is 9, but 9 is not represented in this code. The largest positive value is 7. Okay, so what happens if I have this result 9? Of course, a normal ALU is a full adder. It simply adds 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 1 is 0, 1 carry, 0 plus 0 plus carry, 1. Okay, and the final result, if I take this value as 2's complement value, this is minus 7, not 9. And of course, this would be catastrophic error because I have, for example, some kind of automation control or whatever. I'm driving a car and instead of turning the wheel to the left side, I turn the wheel to the right side because I have missed the proper sign. So instead of having +9, I take -7 as a result of this operation. And this will be catastrophic, so for that reason, the best solution is to take the value of 7. The largest possible positive value would be more meaningful than -7. And this saturation is automatically supported at the hardware level. So you simply activate this saturation mode, then after that, all of the ALU instructions are performed with saturation. The same is for the negative side. So if I add two negative values, and if this sum exceeds the largest negative value, it is automatically saturated to the most negative value. In this case, it will be -8. -8 is the most negative value for 4-bit 2's complement number. Okay? It says here, so instead of having -7, you take then the largest positive value, that is +7. Okay. Then there is also the issue of rounding, and this issue of rounding, we will discuss it in the context of multiplier. We have shown this. So going further with this multiplier unit, more or less it has the same conceptual architecture. Again, it is like a binary operation. You have X branch, Y branch. Again, you have two registers, MX0, MX1, MY0, MY1, which can be selected as input arguments for multiplication. These are 16 bits argument, and they can be treated either as signed numbers or unsigned numbers. So as an additional flag of assembly instruction for multiplication, you designate whether the first argument is signed or unsigned, whether the second argument is signed or unsigned. And based on this, it knows how to interpret this data, because of course it must know whether it is really unsigned number or if it is signed number, the interpretation of the first most significant bit in the register. Okay. The same as with ALU unit. As a left side argument, I can use result bus. So for example, AR, output of ALU unit, can be used as a 16-bit left side argument for multiplication. And the same as a ALU register, the same as ALU unit, I also have feedback register for the right side argument. This feedback register is 16 bits wide, and of course it is then the question, which 16 bits of 32-bit product I use? Because the product of two 16-bit values is 32 bits wide. So if I want to store the product into feedback register, then the most significant part of the product, these first 16 bits, upper 16 bits, are stored in the feedback register. And these lower 16 bits are discarded. Why I say? Because the default mode is fractional mode. So in the fractional mode, of course, the most significant part is in the upper word. And the lower word is, let's say, less significant. Just to illustrate another thing. So this architecture here is based on 16-bit arguments. 16. But maybe you would need also multiplication of two 32-bits number. So how to do the multiplication of double word arguments? 16 plus 16 times 16 plus 16. In this case, it can also be done, but with 4 multiplication and additions. Because you can combine, first of all, these upper words, for example, A high, A low, B high, B low. So first product would be A high times B high. A high times B high. result that is 32 bits wide. And that is the most significant part of the result. Then I have these two cross products. I have the product A high times B low, as well as B high times A low. Okay? These two cross product terms, they are, with their weight, 16 bits less significant. So when aligning them, I shift them to the 16 bits to the right. So these are two products, A high times B low, and the same thing in A low times B high. And as a final factor, you have A low times B low. And this one is shifted 32 bits to the right side. A low, B low. So if I add all this together, I get the 64-bit result, as expected. So I get the product of two 32 bits number using 4 multiplication and 3 additions, which are weight adjusted. So each of these terms is properly weight adjusted. So just to be able to understand, so if, for example, these two input arguments are signed, 32-bit signed fractions, like Q 1.31 times Q 1.31. So how should you interpret the arguments for this multiplication? So when do I use sign as an input argument, and when do I use unsigned? For example, this here, high times high. So how do I interpret these two arguments? Sign, both sign. So this will be sign, sign. This here, if I take A high times B low, it must be signed times unsigned. So the second argument must be treated as an unsigned number, this BL. Signed times unsigned. This one is contra. So unsigned times signed. And finally, unsigned, unsigned, UU. And for that reason, it is necessary to be able to define the argument type for each of the multiply instruction as additional flag, let's say, as additional bit inside the instruction code. And exactly this CPU, this DSP, it has 2 bits in the instruction code, which are used to define the type of the argument. Okay? Okay, so this was just a discussion why it is important to have this signed or unsigned flag for left and right side argument. So once I have this 32-bit wide result, I pass it through special unit that is adder or subtractor. So the idea is this 32-bit value can be either added to the 40-bit result or subtracted from the 40-bit result. So when aligning, these 32 bits are aligned with these two registers, MR0, MR1. So they are aligned with these two. But this MR, it has also additional register MR2, which is 8 bits wide. Why? Because if I accumulate several products, then I must be able to somehow store this overflow, let's say. Because if I multiply 1 times 1, the result is 1. It means all of these registers are full. MR1 and MR0 are full. So the leading bit, if they are positive, is 0, 1. Leading bits are 0, 1, blah, blah, blah. And if I want to accumulate such products, I must somehow be able to capture all of this carry that goes from the MR1 and MR0. So with this addition, this extension goes into MR2. And if this MR2 is 8 bits wide, 8 bits wide, then it means I can add 256 such products without worrying about the overflow. I have sufficient width on the left side to capture the proper value of the sum of 256 products. And only then, when I have the final result, I can try to find where the leading bit is, 0, 1, depending on the sign, and then shift to the right whatever number of bit position I need to have the value in a single word, 16-bit, or maybe double word at 32-bit. Okay? So that is the purpose of this 8-bit extension. So the 40-bit value is fed back to the adder subtractor. This here can be either added or subtracted from the current value of the accumulator. These three muxes are used to initialize the value from the memory. For example, if I want to write some initial value to MR2, MR1, or MR0, then I use this mux to write the desired initial value. Here, it also has this feedback. So, for example, I can write to MX register, but also I can take the value back to memory. So that is the purpose of this feedback loop. And finally, if I want to store the result in the memory, since this is 40 bits wide, I must select one of the three at a given time. So, for example, I use this mux and say, okay, write MR0 to memory, so emit the value to the data memory data bus, and then write these values to some address in data memory. Then in the next instruction, I take MR1, write it to the memory, and so on. Because the data width is only 16-bit, okay? We will make a break here. Okay, now we are 5 minutes after 12. Do you have any questions? So the idea is all of this is in detail described in the documents which are on the web. I will show them as additional materials for the course, and these are in this part that is related to the laboratory exercises. Okay, intranet. If I go to this embedded system design, 86513, files, laboratory exercises, and then I have first and second laboratory exercises, tools, instruction, work plan. No, it is in the lectures. In the lecture section, first part, second part, additional lecture materials. So if I download this zip file is then in downloads, go to downloads, additional materials, okay. So it has the folder with, I don't know how many, 15 documents. But out of those, I have written which are the most important, which you should read. And this is written here, description of additional materials for the last cycle from embedded system design. So these are the documents that you should focus. And it is what I'm describing on the lectures. So you have the textual description of all of this that I'm describing. Just an example, DSP execution unit, compu. Let's try to find this compu. Computational units, where they have them. First. Okay. So make arithmetic, format, signed, unsigned, allo unit. You can see this. It is the same block scheme as on the slides. All of the instructions which are supported in the allo unit. input and output registers, saturation mode. Okay, then this is for the division operation. It is performed also in our unit. We will not cover this in the lecture, so it is we don't have enough time to cover this as well, but it describes here how the division is performed. So it does not have a single instruction that performs division, but you have to repeat one instruction 16 times. So you get only one bit at a time of the quotient. So you have actually this instruction, div q, and you repeat this instruction 15 times, and finally, the first one is for the sign computation, and then you repeat this one that does the division 15 times, and you get the 16-bit result of the division. Okay, and then it goes to the MAC, to the multiple accumulate structure description. All of the operations supported, so either only multiplication, or multiplication with addition, with accumulation, or with subtraction. And the final instruction is to set the whole MR to 0, all 40 bits. It describes here, because this multiplier can also operate in integer mode, not fractional mode. And that means it interprets the data as the decimal points is to the rightmost place. So, for example, instead of having decimal point after the first bit, as is shown here, now I don't know what to do. I have to put this here. No. So instead of having first the decimal point after the first bit here, or here, the decimal point can be on the right side of the register. And that means that I interpret the data as integer number. And if I want to operate the multiplier in this integer mode, I can. I simply have to set one bit in one of the control registers, and after that, instead of interpreting data as fractional numbers, it interprets them as integer numbers. Okay? Okay, let's make a break. Then we will continue.
En papel.
A mí en papel todo. Todo lo he programado en papel.
¿Qué dices, tío?
Bueno, pero porque si no. Claro, bueno, estos son cortos, que damos un violín.
Ya, hombre, tienen que poner
Claro, nos ponen a
código.
nosotros eso en papel y no
He hecho
acabo yo.
programas
Todavía sigo ahí,
enteros,
¿sabes?
He hecho programas enteros en papel.
Pero de cuántas
¿Qué te digo? ¿De 4 hojas por delante y por detrás?
Pero,
Sí, sí, sí.
pero como lo haces en papel, si yo cambio todo 18 veces.
Ya ves.
¿Estás de coña? No, no, no.
Es que sí, así no se aprende a programar.
Pero si es que encima.
O sea, es que.
Claro, pues entonces
aquí
mirarán.
te sale 8 de 12.
Entonces mirarán, no sé, por supongo que tengas idea, porque no creo que se vayan a poner a pasar ordenador para probar si funciona.
Ya, no, yo supongo que lo leerán un poco.
Claro, como la
leerán
estructura.
A ver qué tal está y entonces, claro.
Miras la práctica.
Sí, que además sí, lo meten en el papel, en el ordenador, te salen 8 errores y esto de que ahora.
Claro, es que. Lógicamente.
Ya me
Qué
dirá.
horror. Ah, no, es que no lo veo.
No.
Los finales, ahí ya tienes 4 horas de examen.
Madre mía.
Pues ahí está todo.
Nosotros, bueno, lo mismo, fueron 3 horas de examen de práctica, que me dieron ordenador.
Claro, es que no sé, se deben pensar que copiamos. Si estamos programando, no sé qué le vas a copiar.
La verdad que
Hombre, pues si copias, copias, se va
Pero
en papel.
y que es igual, porque en el trabajo tú no te vas a aprender a tal. Mira,
Claro.
las cosas en internet, cómo se está estructurando.
Ya,
¿Cómo se
literal.
hace? No sé.
Ah, dices como copiarte de internet. ¿No?
Claro,
Ah,
claro.
Bueno, nosotros que somos, nos dividen en clase, entonces el profesor está todo el rato pasando si no te da tiempo a ver internet, ¿no?
Ya.
Y que lo que te ponen, yo creo que mirando internet lo sé.
Claro, es que es eso.
O como esto, me pongo a mirar internet y
Me quedo
¿qué
igual.
saco?
Yo
Nada.
me quedo igual.
Nada, me quedo igual.
Estuve intentando mirar en YouTube a ver si había ejercicios de algo.
Que va.
Y
¿Qué
no
bien?
encontré nada. Digo,
No hay nada.
vale, ya está. Si es que ya estás, es que. Es que ya está.
No, que nos pongan el de recuperación, teoría y ya está.
Yo, ¿dónde está?
Normal, de la normal. Sí.
Online o, bueno, se lo dice si son de próxima práctica, lo que sea. Dice, oye, que.
Es que me voy. ¿Qué quieres que haga? ¿Me quedo aquí hasta el 15 de julio por tu maestra? Pues tampoco. Yo me voy.
Mira, lo bueno es que si este es el panorama de la clase, la gente que somos
Claro, es
nosotros,
que si no
y
hubiera
un
otra
croata
cosa-
que ni viene. Pues, ¿qué te digo? No nos va a suspender a todos, es que vamos a suspender el 70%, ¿no? Probablemente.
Pero sí que dijo que había muchos.
Claro,
Que hay muchos
sí,
croatas inscritos, pero que ninguno viene porque son repetidores.
Ya,
O algo así.
claro, y son repetidores porque.
Porque se han fumado esta clase ya, vamos.
Vale.
Joder.
Bueno, mira, nosotros venimos a clase, lo hemos intentado.
Por lo menos
Ya
no
está.
son que nos dan nada.
Sí, yo creo que.
Que sí, ya quedan de probar.
Además, la práctica la llevamos bien.
Las prácticas no son.
Porque la práctica
Venimos a
no-
clase, oye, se está intentando. Es que si no me habéis enseñado a hacerlo, no sé hacerlo. No puedo hacer cosas que no.
Es que
Está,
de todas
nada más.
formas nos podían avisar en plan. Este ya es un curso avanzado, ya
Claro.
lo hizo antes, ¿sabes?
Claro.
O algo.
Oye, ¿sabéis hacer esto? No, pues entonces no te metas.
Claro, entonces no te lo cojas.
Sí.
O si ya no lo he cogido, decir, ¿cómo vais de tal? Y dedicar, prefiero haber dedicado una hora más o una clase la primera semana a que me
clase
explicasen cosas.
Me pones una clase extra y.
Que me
Vale.
den más bases o algo, si no sé.
Y todavía me nos va a quedar un examen de ejemplo, porque claro, yo llego al examen y me veo eso y digo, ¿en qué habla me metía? Me digo, bueno.
Es una clasista.
Madre mía.
Ya te digo, chaval. Pero este parece más blandito, ¿no?
Sí, al menos aplico mirada a la cara y eso.
Sí, sí, el otro, o sea,
El otro miraba allí. Y ya.
Que el croata de la clase pasada y no los cogimos porque los exámenes son peor que
Peor que el otro.
Peor que el primero.
peor que el otro.
Mira, eso
Pero
lo
que te cobran un 7 para probar.
yo
Uy. Vamos a ver.
A tope, chicos.
Vamos a suspender, tío, esta no Erasmus. Tengo peor media aquí que en
¿A que sí?
España.
me pasa.
Pero que.
Me pasa que no.
Bueno, en España también se vuelve.
Pero el
Más que
croata,
aquí sí.
Yo tengo más media, te lo juro, tengo más media en España que aquí. Y aquí estoy estudiando más que en España.
Que sí, que sí.
No, me han engañado. Eso no, aquí
Esto
parece
es un tiempo, esto es un tiempo. Luego está la nota de derecho que no hace ni el huevo. Y
Mira,
yo,
mira,
esto no
de
es
verdad,
justo.
o sea, que te
algunas
Pero
prácticas
los
por
exámenes,
ahí
los
parecidas que
exámenes
puedes
prácticamente no
inspirarte.
están resueltos. En alguna asignatura puede, pero
Por ejemplo, el report del lab podría estar o no está.
Podría estar, ¿eh?
joder, sí, definitivo.
Okay, it says here, so multiply, accumulate unit performance multiplication with cumulative addition or subtraction, and with saturation as well if needed. And the saturation occurs only in one case, when I multiply -1 times -1, because the result is +1 and +1 cannot be represented. I have only 0.09999, so the largest positive value is 0.7FFFFFF. So that is the largest positive value. So if the result would be 1, it is saturated to this largest positive value that has leading 0 bit. Okay. Multiplier has two 16-bit input ports, and the output is 32 bits wide, which can be forwarded to this adder subtractor that accumulates the results into 40-bit result. And the final register, the result register, is composed of 3 registers, MR0 and 1, which are actually this aligned with the 32-bit product, and this MR2, which is extension of 8 bits of bit. It has 4 input registers, MX0, MX1, MY0, MY1, and it has this feedback for the right side argument it is MF register, while for the left side argument I can use any of the result registers as a left side argument for multiplication. It can perform multiplication, let's say here, with or without sign. So it has this sign flag in the instruction, just in order to be able to compute this kind of double word multiplication, where you have to take care of the proper interpretation of the input data, whether it is signed or unsigned. It has detection of the overflow, and it has also hardware supported rounding. And I will display this. This is important. This hardware supported rounding. I have example here. Do I have example? No, I don't have example here. So instead of having this flag, signed, unsigned, signed, signed, blah, blah, I put R and D in the brackets, and that means round. So multiply with rounding. In this case, I cannot specify sign, 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 unsigned. It automatically implies sign times sign. So this round automatically then implies that both arguments are signed, and what means that after multiplication, I want to do the rounding. What does it mean? So if I have the product that is 32 bits wide, and if I have to take only the most significant word of the product, okay, so for example, Q1 times 115 times Q115, and the result would be Q130, and the last bit, the 32nd bit is 0. 32nd bit is 0 because it automatically aligns the product 1 bit to the left to get rid of the double sign bit that occurs if you do the integer multiplication. So if you have a normal integer multiplier, then the product of two signed number always has double sign bit. So either 0, 0 or 1, 1. For example, just for illustration, if I have 3-bit signed numbers, so 3, 2, 1, 0, -1, -1, minus 2, minus 3, minus 4. And if I multiply two values, then which are the total value span of the product that can be a result of this operation? The largest positive product would be 9. 3 times 3 is 9. If the product is negative, it can be, for example, minus 12. The illegal product would be minus 4 times minus 4, which is 16. And this 16 cannot be represented as a legal number in the double word format. So the double word format, if I treat this result as an integer product, it has the decimal point to the rightmost side. And this 9 is then written, whatever, 6 bit. So it must be 0, 0, 1, 0, 0, 1. So this would be 9. Okay? And what I see, if I operate in this integer mode, I will always have the same value at the two most significant bits of the product. They will be either 0, 0 if the product is positive, or they will be 1, 1 if the product is negative. Okay? Just for example, if I want to show the case of minus 12, so 12 written as a positive number would be 8 plus 4. So 8 plus 4. 8 plus 4. And then 2 bits to the left. This is 12. Then I do the first complement. And I add 1. And I get the 2's complement. And the 2's complement is then 0, 0, 1, 0, 1, 1. So again, you can see that this product minus 12, it has two leading ones. I have two sign bits. And if I want to operate in the fractional mode, this is annoying because otherwise I would have to left shift the result by one position to have the decimal point exactly here. This would be, sorry, not here, but here. So I want to move the position of decimal point from here to here. This would be the proper interpretation of the most significant word of the product if I only have to take the upper word. So not this, but this. And to have this, I can simply shift the product to the left by one position and then extract the upper word. And it is done automatically in hardware. So because in this multiplier, by default it operates in this fractional mode. It means that automatically after multiplication, the product, the integer product is shifted to the left by one position. But if I want to operate in integer mode, and then I have to change this bit, control bit in one of the control registers, and then it deactivates this left shift. It operates as a conventional integer multiplier. Okay, so if I want to take this upper word, I use this fractional mode, which means, okay, it will be left shifted to the left by one position. It means I would get exactly the desired value as the output. So how this value is interpreted? This value here is written as 0, 1, 0. So this one has the weight of 0.5. This one has the weight of 0.25. So actually, the value that I get is 1/2 what is written here. And is it correct? No, because the actual value, I ignore this one here. Originally, what I wanted to compute was 9, what was 0.75 times 0.75. That was what was supposed to be computed. And of course, the result of this operation is not 0.5. 0.5 is only if I truncate the lower part. I approximate this product with the upper word, and this upper word, result of the upper word is 0.5. If I compute this, then of course this is 0.5 plus 0.062 blah blah. So this is 0.125, and this is here is 0.06, I don't know, blah blah. So this part is missing here. This is what I truncate. I get rid of this, I take only the upper word, and I make the error. And then this error is always negative. And the largest magnitude of this error is whatever is thrown away. And this, what is thrown away, is practically the same value as this last significant bit. So this least significant bit, LSB, of the upper word, it has almost the same weight as if all the lower bits are set to 1. So 1, 1, 1, 1 is only a little bit smaller than the value 1, 0, 0, 0. Okay, so that is the largest error that I do. I do by truncating, by simply discarding this part of the result, the error that I make is practically either 0 or up to, at most, -1 least significant bit of the upper word. That is the error that I do with truncation. And instead of truncation, which always results with negative error, I can do the rounding. And in this case, the error would be half plus minus least significant bit. So the rounding would be by asking ourselves whether this reminder is greater or less than half. So if it is less than half, I can discard it, because in this case the error would be negative, but at most 1/2 of the least significant bit. But if the reminder is larger than half, which means that the first bit of the reminder is set to 1, or the lower word is set to 1, it means that this part that I'm truncating is larger than 1/2, and it is better to increase this value by 1. It is better to increase the value of the upper word by 1. In this case, the error is now positive because the value is larger than it's supposed to be, but it is at most 1/2 bit too much positive. Okay? So it is better to have this symmetrical error, plus or minus 1/2 bit, than to have always negative error up to 1 least significant bit. And this rounding is also done in the same cycle where I do the multiplication, if you desire. So if you desire, automatically the product is rounded, which means that this value, this lower word, is rounded into upper word if the lower word is greater than 1/2. So you simply add 1. So this rounding can be done by simply adding 1/2 to the register. So if I add this value, 0, 1, 0. If I add this value to the upper value, what do I get? I get 1 here, I get 1 here, and 0 here. I don't have carry. In this case, I don't have carry, because this reminder is less than 1/2. But if, for example, this bit is set to 1, in this case, I get 1 plus 1 is 0, 1 carry. Then I increment the upper word by 1. So by simply adding 1/2, I do the rounding. So I add this value to the result. And then discard the lower word. Okay? The final question is, what to do is if the product is such that this reminder is exactly 1/2. So it means that this first bit is set, and all of the remaining bits are 0. So if the result is exactly midway between two values of the upper word, lower value or upper value. So you don't know what to do, to add 1 or not, because it is exactly midway. And then if you do always a rounding up what is the case if you add 1/2. If I add 1/2 to 1/2, it is 1 whole. So automatically you get the carry if it is exactly midway. But is it fair to have always up rounding when the actual value is exactly in the middle? So the idea is it is not fair. And this kind of behavior can introduce bias. When you have this repeated rounding up of the midpoint value, it can create the bias in the final result. And then they say, why don't you do some kind of unbiased rounding? So only in the case when this remainder is 1/2, toss a coin. And based on the result of this random experiment, either round up or not. Okay, so that is the idea, to have an unbiased rounding only for the case when the remainder is 1/2. And how to do this coin tossing? For example, like a random generator of 1-bit value. They say, maybe this bit here would be a nice random generator. The least significant bit of the upper word. It is some value, sometimes 1, sometimes 0. Let's treat this bit as a random generator. And based on this value of the least significant bit of the upper word, decide whether we do up rounding or not, but only if the remainder is 1/2. If the remainder is greater than 1/2, we always round up by 1. Only if the remainder is 1/2, then I check this bit here. If it is set, I do rounding. I do addition by 1. If it is not set, if it's 0, then I don't. So actually it rounds to even. So if the remainder is 0, then if it is exactly 1/2, if the remainder is exactly 1/2, and if the upper word is even, you don't round up. And if the upper word is odd, then you round up, again you get the even number. So it is always round to even if the remainder is exactly 1/2. And that is the way that this unbiased rounding is implemented on this DSP processor. It is said here something like I don't have it here. This here is a syntax of the multiplication operation. So all possible combination of multiply instruction are multiply result is equal to multiply result plus x operand times y operand. It can be without this accumulation, so it can be MR equal to only this here. So this is example for the instruction with accumulation. Then what is this x operand or y operand? This x operand here is written here. So mx0, mx1, and any of the result registers. It's nice that I have 8 combinations here, so 3 bits in the instruction code are sufficient to encode the left side argument. So either one of the 2 dedicated input registers or one of the 6 result registers. Then for the y branch, for the y argument, it can be my0, my1, or feedback. So 3 combination. Again, I use 2 bits to specify the y side argument. Finally, this instruction can also be executed conditionally. And this table lists all 15 possible combination of conditions. Okay, so equal, not equal, greater than, greater or equal, less than, less or equal, negative, positive, overflow of allo, not overflow of allo, carry, not carry, blah, blah, blah. And so I need then 5 bits to encode this condition, since the last combination is unconditional execution. Then, then 16 combination is 4 bits, sorry. 4 bits because it is 16 combination, okay. And then I have example here, if greater or equal, MR is equal to MR plus MX0 times MY1, and both arguments are treated as signed numbers. Or another example, unconditional execution, mr is equal to mr plus mx0 times mx0. So the second argument can also be x combination. It is like for squared value. So to compute the squared value, I don't have to set both arguments, the same argument in two registers. I take only one register mx, and then this mx can be also used as a y side argument to do this squared value computation. Okay, and another few examples, mx times my, ar times my1, accumulation plus ar times my1, or initialization to 0, or special instruction if multiplier is overflowed, so if overflow occurs, then saturate result. And what does it mean when this MV is set, when this multiplier overflow occurs? It occurs when the result in this two lower register is not consistent with the value in MR2, which means, so if MR1 is negative value, if the whole register, okay, if the result in MR0 and MR1 is negative value, it means that the first bit of MR1 is 1, negative. And in this case, MR2 must be all ones, which means that MR2 is nothing else but sign extension of MR1. If the MR1 is positive value, so the first bit is 0, then MR2 must be all zeros. If this is not such, then it's overflow. So only if MR2 is sign extension of MR1 and MR0, only in this case I don't have overflow. Otherwise, it's overflow. And in this case, what it does, if this value is positive in MR2, MR1, and MR0, then the largest positive value is written in these two registers. So 7 FFF, FFFFF. If this value in the whole 40-bit register is negative, then the largest negative value is written, and that would be 80000000. Okay, so that is the meaning of this saturation instruction. So if multiplier is overflowed, then saturate result MR. Okay, this here is example of conditional execution where I treat both values as unsigned. Finally, what I also have to describe is what is the meaning of this shadow, this black shadow here, and black shadow here as well. The same is for the feedback register. The same is for the ALU unit. I also had this black shadow here, black shadow here, black shadow here, black shadow here. What it means, it has like a mirroring set of registers. There are actually two sets of registers. And one are like a background set of registers, one set, and the other is like foreground set of registers. And I can toggle one single bit in one control register of the CPU to exchange these two sets. So black becomes white and white becomes black. Why is this useful? It is useful to handle context store when servicing the interrupt request. So when you have, for example, some interrupt request, you don't know what the processor is doing at that time. Interrupt occurs, you have to do something, you have to use registers, but you don't know what is actually currently in the register, if it is important value or not, because the program, the main program is using this register as well. And then what you can do, you can, on conventional CPU, you do the context store, which means you push the values from all the registers that you'll be using on some stack to store them in the memory. You use the registers, and then later on you pop these values, you restore the values from the stack back to registers originally, what the value was before the interrupt was involved. And all of this context store and context restore takes cycles, because you have to write this value from registers to memory, to to the stack, and later on read from the stack back to the registers just to restore the original values that were used in the main program. And it takes many cycles if you have to use many registers in the interrupt request routine, because you have to store all the values that were in these registers when the interrupt occurred. And to speed up these things, the idea is why I don't use like a temporary set of registers just for the servicing of interrupt request routine. And this temporary set of registers are these shadowing registers. I simply swap the main set of registers with the shadowing registers. I do the desired interrupt service routine and then swap back. And this swapping is instantaneous. So only one cycle is sufficient to do this swapping of these two registered banks. This mirroring is then the most fast way to do the context store, but nevertheless, it cannot be nested. So when you have the stack, then another interrupt can interrupt the current interrupt service routine that is being processed. So like a nesting of the interrupt requests. This cannot occur because you only have one set of shadowing register. So if immediately, as you enter the interrupt service routine, you have to disable further interrupts from occurring, service interrupt, and later release this register back to the original value. Okay, but for most of the application, this kind of interrupt servicing is much faster than the conventional stack-based context save and context restore. That is the reason why they have this shadowing set of registers. Okay, then going further, we have 15 minutes more just to explain the shifter unit. It is the last unit that we have to describe of the three execution units. And this shifter is special shifter. It supports so-called barrel shifting. Because with conventional shifter, you only shift by one position, to the left or to the right. So you have shift left, shift right, or rotate left, rotate right, but only one position. And in some signal processing application, it is usually desirable to have multiple position shifting. Maybe 3 bits to the left or 5 bits to the left, whatever. So to be able to shift the value by any number of bit positions to the left or to the right. This architecture is then called barrel shifter because as a revolver that has this barrel, you can rotate this barrel by any position and have a new position of this barrel on your revolver. The same idea is here. So this rotation can be arbitrary number of positions to the left or to the right, and then you get this shifting in a single cycle for any number of shifts to the left and to the right. And how is this performed? It is actually, instead of really using a shift register, because shift register is nothing else but a set of flip-flops, set of D vestibules, which are connected Q to D, blah, 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 and which are run with the same clock signal. So this is the way that shift registers are implemented on a conventional microcontroller or CPU. By applying a rising edge here, I simply transfer the value from one vestibule to the other. Okay, in this case, this barrel shifter is implemented using multiplexer. Why so? Because, for example, let's say that this is 3-bit value I want to shift, 101. And the result would be double word shifted value or whatever. So this is, for example, 3 bits, okay, single word value, and I have 6-bit result register just for illustration. And for example, I want to shift relative to this position here, to the lower word, but 2 positions to the left. Then means that I would have the value here, 1, 0, 1, 0, 0. So I want to shift from the left side 2 zeros, and this would be 0. Okay? But what here I actually have a multiplexer which says which of these 16 bits, which of these 3 bits are forwarded to this position. Another multiplexer here. Which of the 3 bits are forwarded to this position? So I simply select what is the source for this value. And of course, if you have 16 positions for each of the bits, you can directly transfer any value to any position by using simply a multiplexer. So instead of shifting by 1 position, by 1, 1, I simply say from here to here, from here to here. So it is like a matrix, like some kind of crossbar matrix that decides which bit is shifted to which position in the final double word result. In the actual implementation, the input register is 16 bits wide, 16 bit, and the output registers are 32 bits wide, so 16 plus 16. Exactly it's here, but each of these are 16 bits wide, okay? When shifting, you must say, do I shift relatively to the lower word or relatively to the upper word? Because you must specify the reference. For example, as if I would put this S input register to SR1 and then shift left or right by given number of position. Or as if I would put S input to SR0 and then shift left or right by any given number of position. So you must specify the reference either high or low. So this reference is also one argument of this shift operation. So whether do you align this input with the upper word of the output register or with the lower word of the output register. Then, for example, if I want to do double word shifting, how would I do this? I have 32-bit value, A high and A low. And I want to shift it to the right by 5 positions. Then, in this case, I would take, for example, first the higher word, shifter input is equal to H, this one. And then I would say, okay, S result is shifter input. I will say here by -5, but actually this value comes from either a register, how many positions to the left or to the right, or as an immediate value encoded in the instruction code. This by -5 would be example of immediate value defined in the instruction code. So shifter result is shifter input by -5, but I say reference high. And that means that this here is 32-bit. And this here is 16-bit. Okay? So as a result, I get, after this instruction, this H high, I get 5 0 bits in the upper register. Then I have this HR. Out of this HR, 11 bits are in the upper result, SR1. So 11 upper bits, 11 up, doesn't matter. 11 MSBs of HR. Then I have this five least significant bit. This here is 5 LSBs of HR. And finally, I have another 11 0 bits. Okay, 5 0 bits, 11 bits of HR, then 5 bits of HR, and 11 0 bits. So I have shifted this value 5 positions to the right, but I get the 32-bit value. Now what I want to do the same thing for the lower word. But in order to place this A low over this 11 bits in the lower word, what do I have to do? I must retain this value from before, from the first instruction, from shifting of the upper word. I must combine the result of shifting of the upper word with shifting of the lower word. Okay? And this combination is done how? By OR operation. By simply ORing the result. So if I take the original result of the first instruction and OR it with the result of the second shift of the lower word, again by -5, but relative low instead of relative high, then I take this value, place it above this 11 bits of the result. I get rid of these 5 bits which are thrown in the garbage, let's say. The last 5 bits of AL are thrown in the garbage. And then I simply OR the result of the second shift with the result of the first shift. So this ORing logic is shown here. It can be activated or not. So if I activate this ORing logic, then simply the 32-bit result from the previous shift is fed back to this OR logic, which is combined to the 32-bit value of the current shift. So for example, if I performed first the upper word shift, I have this result across both of these registers. So 11 bits here and 5 bits here. Then I feed back this result to this OR pass logic and combine it with the result of the lower word shift, where I simply place the 11 most significant bits of lower word over 11 least significant bit of SR1. So this OR logic enables this combination of two shifting operations. So for the first operation would be relative high because this H high is the upper word, and for the second shift would be relatively low because I want to align this lower word with the SR0 register and then shift it to the 5 position to the right. So that is the usefulness of this reference. And this value by -5, it can come from this register here, shifter element. So shifter element, 8-bit value, which is 2's complement value from -128 up to 1 plus 127. This value can be passed as a control value to the shifter array. So it says here how many positions to the left, how many positions to the right, or to the right. If the value is negative, it means to the right. If the value is positive, it means to the left. So this shifter element defines how many positions to the left or to the right I want to shift. Okay? And alternatively, this value can come from the instruction. From the instruction, where do I have this combination? Here, from the instruction. So this immediate value by -5 can be written in the instruction. In this case, this control input of the shifter is driven by this constant in the instruction. Okay? Just few examples. Also, the shift can be arithmetic shift or logical shift. There is a difference how do we interpret the first sign bit. So if it is arithmetic shift, then I have to interpret first bit as a sign bit. And if shifting to the right, I have to simply repeat this sign bit from the left side. If it is logical shift, then I simply always insert zeros from the left side if I shift to the right. Okay? So that is the difference between arithmetic shift and logical shift. There are two different assembly instructions, one for the arithmetic shift, the other for logical shift. Sorry. And so it says here, is this input is shown here, 16-bit at the top, then arithmetic shift by -4 relatively high would simply repeat this first bit 4 times, then copy this input word. These 20 bits, the 12 bits are in SR1, and these 4 bits are on the top of SR0. Okay? If it is logical shift by -4, so 4 bits to the right, relatively high, then you always insert 0 from the left side. And if, as a last example, logical shift by -4 relatively low, it means, okay, as if I would place this value here and then shift it logically by 4 positions to the right. Okay, so this reference is always either high or low. And final example is so-called normalization. It has one instruction that computes how many leading ones or leading zeros do you have, or how many times you can shift to the left until the value is normalized. It means that the value is between 1/2 and 1. So I would like to normalize the input value in shifter input register. How do I do this? How do I do this? I shift it to the left until I get rid of all of the repeating ones or all of the repeating zeros at the top of the register. As long as I'm able to shift out these ones or zeros, I repeat this shift to the left. So in this case here, so this value is negative, but it is not normalized, because if it would be normalized, then the second bit would be 0. So negative value that is greater in magnitude than 1/2, so less than 1/2 negative, would always have 1, 0 something. If I have 1, 1 something, it means it is negative, but in magnitude less than 1/2. So I could shift it to the left at least by 1 position, because it is not normalized. So I actually want to count how many leading ones do I have, or how many leading zeros do I have if the value is positive. In this case here, this result of this normalization would be -2, because I have 2 extra ones. So theoretically, I could shift it to the left by 2 positions, and only then the value is normalized. Okay, the number is negative. And this instruction is not shown here. This instruction computes the exponent, the binary exponent of the input value, and this binary exponent would be -2. So theoretically, this value could be represented with this part here, 1, 0, blah, 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 times 2 to the power of -2. So actually, this here is the normalized value, 1, 0, blah, 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 times